nanohub.org.
Online simulation and more for nanotechnology.
So we'll get started today. You remember from in this semester, we had been talking about, of course, data analysis and design of experiments. And in the beginning of the semester, we talked about that how once you have the results from an experiment, even if you did not design the experiments yourself, then how do you clean the data? How do you plot the data? How you analyze the data? That's what we saw. And next, we talked about how to design experiments. How to design experiments so that the data that you get are really useful data. It samples the space, the problem space correctly. So that we spent quite a bit of time. So that would be the first 10 lectures out of the 15 that we have. And in the last lecture, we talked about big data. And in a big data, you really don't design anything. There's no design of experiment. But the experiments are going on all the time, in the sense of actually clicks on the web or, the pictures that you take. So there is no question that motivated those set of experiments. It is just a sensor data. And then the important thing is there, learning to ask the questions. And one of the questions in big data that you often use is classification. That especially for recommendation system or advertisement, the idea is that if somebody like you, if they can identify, the company can identify that you are like somebody else or you are like a group of people, then they can recommend to you what the people in your group, whatever they like, they can recommend you. And if you buy it, good. So the first approach we talked about is singular value decomposition. Singular value decomposition is a very powerful technique. As I said, that in the beginning of the 19th century, early 1900s, singular value decomposition has been around since then. And they are often used when you want to send the data in sequence. And then you can do classification, you can do image approximation, you can do data transmission. So singular value decomposition has wide variety of uses. Today, I want to tell you about something about what has become known classically as machine learning, but it is a smaller group. The idea is that what I'll be talking about today does not require singular value decomposition and is often much faster, less accuracy, but faster. And that's why when you are on a page, you are looking for something, within the fraction of a second, they have to show the recommendation because otherwise you'll go to a new page. And so this speed is why some of these things, new algorithms, are so useful. So as I have mentioned as I just mentioned a few minutes ago, there's a recommendation or the advertisement industry or in the Netflix recommendation and this type of classification of big data. All the 4 lectures that we'll be talking about has to do with this type of classification problem. Now, in the last class, as I mentioned that once you have the big data from the cloud, then the initial part is the data processing and all. So the last lecture was about principal component analysis and the singular value decomposition. I explained using very simple algorithms, very simple examples, numerical examples, how the method works. And you'll be doing a homework related to that where you'll be uploading your own picture and see how many singular value do you need in order so that a friend can recognize you. Because of course you can recognize yourself within probably half a pixel. But now I'm going to talk about this part. Today's lecture has to do with regression and classification. Today's and tomorrow, next lecture, this 12 and 13. In 14, I'll be talking about a little bit of this, and also physics-based machine learning. Because you see, machine learning is getting out of control. And I think most people realize that if you don't do something dramatic, then first of all, none of the engineering problems, Machine learning would be useful for none of the engineering problems because you cannot extrapolate machine learning information. So what is the problem? Always important thing is to think simply. So you remember this is delta y is the output and you have a set of input. And the input could be variety of things. It could be temperature, it could be relative humidity, it could be hours spent in studying for an exam, and delta y could be your pass and fail for the exam. And the goal here is, in this case, the goal here is to determine f that connects delta y to the input. Now, often we have f could be a differential equation. F could be a differential equation where the solution is delta y and input could be, for example, some x. So that's why your f could be solution of a differential equation. But often f does not have to be a solution of a differential equation. It can be a curve fit. You have a bunch of points, you fit a line. And in that case, f is simply a fitting function. But in all those cases, f is what we desire. And machine learning's goal is to calculate f. What is that f? When you don't know physics. That's what is machine learning tries to do. Now, as I said, it could be pass, fail, it could be the grades. A student gets A, B, C, D, E. It could be grade points. So there can be different levels of granularity in y. Y doesn't have to be a continuous function. I mean, it can be like grade points, but it doesn't have to be. It can be a certain class. And remember, we are very interested in the classification problem. That's big data is a big deal there. And fx can come from design of experiment. Remember, the design of experiment was to determine the optimum combination of experiment that will maximize or minimize a function. So that was also all about calculating f. So today we'll talk about f, but I will do it by using a specific example. And if you follow through, you will understand every step of it because it's very simple. By the way, all the headlines that you see, underlying all those headlines is actually a very, very simple algorithm. So that's what we are after. You should not be too concerned when you hear or look at this and say that you will not understand it. There's nothing sophisticated about it. There is sophistication. I'll explain where the sophistication is, but the concept is actually very simple. So let's take an example. And I took it from one of the examples that was in the Wikipedia, but I worked it out in a different way. So let's say that you have a group of students who have studied different number of hours for an exam, and some of them have not passed, some of them have passed, and others for sure have passed. So this is a simple classification problem. How many hours do you need to study so that you pass the exam? Now you can see that it is a sort of a little bit not 100% sure. What I have done here is that I have taken those students, and the x-axis is number of hours they studied. And if they studied very little, then chances of passing the exam is small. And if they studied very hard, then the chances of passing is high. But of course, in between, you can see that there are regions somebody didn't study as much. Then they still passed. And this is that point their friend says that he is a genius. And then at this point, they studied hard, but didn't really do that well. And they passed. And so there is a transition region between the class. Now, this would be called a level problem, because very soon I'm going to talk about supervised problem or level problem, because you know what they did at the end of the day. You know that whether they got a 0 and a 1 as an output. So therefore, if you had A, B, C, D, E, then it could be 5 groups of experiments. So, and if it is a continuous, it will be a distribution function, as you know. So it will be a distribution function about full, fail, Weibull, and all distributions talked about. So this is a reduced version of the distribution. All right. So therefore, if somebody asks me to classify that how many hours do you read, you see, it's not rocket science here, right? You say, well, I don't know, maybe so many hours would be a good idea. So many hours. And how much hour that would be? Maybe 2.5 hours. If you study for the exam for 2.5 hours, that sort of looks like the people who do it less is good, is in trouble, and the people who do more is not in trouble. You can see just by looking at the one-dimensional data, you can immediately classify. But the problem is that often you'll have humongous million-dimensional data, and you cannot really do it by hand. Moreover, you can see that if you do it that way, you will do injustice to these points, because of course they passed. And you just said that if you just put an arbitrary threshold here, then you see you are saying that after doing 2 hours of study, it's impossible to pass, which is not correct. So you have to do a little bit more in order to do the classification. So how would you do it? How would you teach a computer to do the classification? Labeled data. Unlabeled, I'll come to in the next lecture. I'll give you unsupervised, how to do the unsupervised classification a little bit later. But today we'll be talking about classified. That means you know who is red and who is blue. Now, what you can do if you want to teach a computer how to do it, you will say, okay, I will take a point T0 and I know all these other points. And I will only, let's say this is the threshold. You say so many hours you study, then you pass. Then I will only take the points which are mislabeled and call that's my error function L. Because only ones that are mislabeled is sort of getting me into trouble. So therefore, if my point is here, then I will write T minus 1 because that's mislabeled. And how many rate points do I have mislabeled in this case? I have 2 rate points which are mislabeled. So I will have that term, and I will try to shift that point left and right, the T0 left and right, until L T0 is minimized. Then that will give me the minimum point. Of course, you can see if I shift it at this point, then I will have number of mislabeling is changing, right? Because you will have the mislabeled one now this is no longer mislabeled. Only this one is mislabeled and that one is mislabeled. So you have, instead of 3 points, you have just 2 points. So what you do is you just shift the threshold point left and right and try to minimize the function L. How to do that? That's where the computer scientists come in. That's where they have to sort of write very sophisticated algorithm that can do a million of these dimensional things. But this is underneath, this is what they're doing. Classification that's what it is. And so the algorithm, lot of work, lot of sophistication. Physics is this. Alright, so let's say you have done that, and what it will give you is sort of a step function. And that is the green line. Let's say you have done it, and then this is sort of, so you have mislabeled 1, mislabeled 2. At this point, you have done this at this point. Now, why did I draw this green exactly there? Because I know the answer. So that's why I did it. But I have told you already that these points are misclassified. So just doing a step function is not a good idea. By the way, I want to, before I move on and explain that how to account for this misclassified one a little bit better, what I want to tell you that it will immediately tell you that how the regression and how the classification problems are closely related. For example, if you take this data points, number of data points, and this is the number of hours studied, and let's say this is, or some other thing, let's say some other output. So then you can do what you can do is you can draw a straight line. And you know how we do the straight line. We do the error, and Ti is the real value, experimental value, quote unquote, and T is the function that you want to fit. And we try to minimize the error. And in this case, every point is important to me. Every point is important to me. That's why I don't want to, my prefactor here is 1 when I do error classification. But let's say when you want to do, it may be that when you are looking for the experiments, some of the experiments are coming from a group which are very reliable. Very reliable. And some of the experiments are coming from a group which is not very reliable. Let's say you have combined data from different labs. In that case, what you want to do is for the rate points, you want to get a little less weight because they are not all equal. So if you do a little less weight, then of course it will try to follow the blue points more. So therefore, you can put a weight here in order to give you the confidence that how much how good the data are. And the classification is the extreme end, where you say only the misclassified one matters, and the ones that are on the left or on the right, which have been correctly classified, has the pre-coefficient equal to 0. So because you are not worried about them, they are in the correct group anyway. So there's, in that sense, this is just a generalization of the error function that we have done before. Now, how would you then account for the misclassified one? Well, one thing you can say, well, what I should do is to take the last point which has been correctly classified and the first point which has been correctly classified in the blue, and simply draw a straight line. Because you see, at least this one, what it says, that this blue guy had at least some chance of passing. It's not 0. Of course, it's binary, so it will be either 0 and 1, but at least it gives you the probability. And this one also says, yeah, it's not probability, is not 100%, but rather it has a certain percent, maybe 60%, but actually the person failed. So there is some chance that that person will fail. And this straight line accounted for the fact that this is. Of course, if you want to do it this way, that's perfectly fine. You can do that. But that you can immediately see that depends on where this point is, whether this point is farther here or here. It will sort of becomes a little arbitrary. So one can do a little bit better is instead of putting a straight line, you put a function which goes like that, and put that one is a sigmoid function. And this sigmoid function is widely used. The purpose of the sigmoid? Well, the purpose of the sigmoid is this T0 is a point where it transitions. T0 is a value which sort of partitions it, and this beta tells you how sharply it turns on. So if it is like a delta like this, then you can see that the beta would be very, very small, so that, or very large, so that it can sharply turn on. If it is somewhat, so that will essentially account for these misclassified points and will get you a line through it. So what is the goal then of the classification? Classification, one way to frame it is to find this function so that you can get the T0 and you can get the beta. It's a non-linear curve fitting. You have a bunch of points and you want to sort of describe those points with a class, and this one sort of gives you those two classes. Yes.
Doesn't matter how many points that we have at that specific time. Let's say at T, these 2 points, yeah. If I have the same point,
yes,
like the same time, 3 or 4.
So therefore you can see immediately that this function will know that. It will sort of,
go down.
It will go down because it is saying that the probability is not 0. So it has to sort of, it will go down like that and then go like that.
To account for that.
Do you account for that? Yeah. Right? So this is a 2-parameter function, just like we said, 2-parameter distribution. Do you remember variable this and that were all curve fitting? This is that same curve fitting. But it is very important. This function also tells that if there is some misclassification far away from this, it will not be too much affected by it because it's sigmoid. So therefore, it doesn't get overly excited. You know, some people have even temper. So this sigmoid function has even temper that few data points here and there would not cause it to fluctuate rapidly. Remember, discrete data and continuous data. That's why we also discuss this notion of not getting overly excited. Median doesn't get overly excited, right? Average does. So therefore, sigmoid function is used that way. All right. So let's do a little bit more how this is done, the mechanics of it. You got the basic idea. In fact, we could end the class here, but let's do a little bit more and to see. So what you can do is essentially take this function, right? These are my values. Now, as you know that, not double. As you know that if you have to do a nonlinear curve fitting, you try to make it a straight line. And then the curve fitting becomes easier. Can you make a straight line out of it? Well, if you do 1 over sigma, then it will go upstairs. Minus 1, this one is going. Take another log. So you can see this will become a straight line. So therefore, instead of working with these variables, you can just simply take sigma. Sigma is a value that you are waiting for, right? This is your y value. So you can take all those sigma values and then essentially try to fit this curve. And if you fit this curve, then you will get 1.50 hours. That is on the mean, T0. How many hours you have to study? So in order to, on average, not to fail. and then you will get the standard deviation, you will get the width of those, 4 hours, because T naught is 4 hours, intercept is 4 hours. So you will have to study on average this 1.5, 2.71, that is the total value. So you have to study about 2.71 hours. 2.71 hours, because you see this 2.71 hours on average in order not to fail, and this gives you 1.5 hours sort of left and right. It sort of gives you the width of that region. Right.
So, Professor, in reality, you would fit T naught, or you would move T naught till the error is minimized?
Right. That's one way. You can write a little code, just error minimize. But here what you do in your sort of transforming that equation, nonlinear equation, into a straight line, and here you just will say lin fit or something in the, throw it in the MATLAB, and it will get back you a straight line fit. And then that will also give you, it will give you comparable numbers. So this is two different ways. Two different.
You know T naught, like initially
I don't know T naught. I have to fit, because you see, this one is the result of the fitting. What I know is this part. I also don't know this, I don't know this, I don't know this. So I will say I have this value, I have Ti values known. And my goal is to coefficient, y is equal to mx plus c. So this m and this c is my output. And from once I have the output, in order to put it in this form, I have to take 1.5 as a common. So that becomes t minus 2.71. So that's the out, right? This is another algorithm, another way you can do the calculation. Let's do another way. Oh, by the way, so this is, you already have learned the first machine learning circuit, because your first machine learning, what is your input? How many hours you studied? What is your sigma function? Processing function, f function. That's your this function. Because as soon as this function is given, a new student comes to you that how long should I study in order to pass this course? Let's say 606. How many hours? then you can put it in this equation and then tell you that whether if you study that many hours, what is your probability of passing the exam, right? So therefore, this is your new machine learning algorithm. Now, of course, you can see that it has all these pieces. This is the sum it does when you have multiple variables. I'll go explain that in a bit, because you have one. So therefore, we didn't have to sum. It requires a threshold, and you remember that threshold 2.71 is my threshold, and so on and so forth. And very soon I'll show you that you may not have just one input, a number of hours studied. You may have many inputs. How good the professor was, how good your friends were, and so on and so forth. And you may not have one layer, you may have multiple layers. Why they are the case, I will explain that. And this will tell you at the end whether you will pass or not. Right? So this is the same thing, but more sophisticated version of this. Alright. It turns out that this is not exactly the two methods I explained to you, that error and the straight line fit. That's not how it is actually done in reality. What is actually done is, what does it remind you of? I have written it here. What does the MLE stand for? Maximum likelihood principle, right? You remember that. And that was, I said, that is much better because it does not assume Gaussian error on both sides. And that's why it's a much better curve fitting tool. So let's take a look for 1 minute about how this one is different from the maximum likelihood. Do you remember that when we were doing that before, then I had the L naught, and L naught was the product of the function evaluated at every point. Do you remember that? F1, F2, F3, and then so on and so forth. What I did not have at that time was this yi. Yi I did not have, and also 1 minus sigma I, 1 minus yi I didn't have. Anytime you want to do binary classification, then you have to write it this way. If you want to do, remember previously every data point was important, and it was not just two classes. This was STIP, all the distribution function. So therefore every value function was equally important. But now I have to project it with yi and 1 minus yi. And similarly, if you have 5 groups, then you will write 5 of these functions, grades A, B, C, D, E. Then you will write 5 of this function. If you take a log, this is what is minimized actually. If you take a log, you can see that yi log of sigma and of this, and that becomes so. This is really the error function that they minimize, and output would be the same. Output would be the same. Output will again be a T naught and the beta. This will be exactly the same answer. So let me explain to you how that is done. It's clear, right? How you sort of understand that if you do d alpha, that will give you the T naught value. Alpha is the T naught. And then beta, well, beta is the slope. So you take a derivative, so therefore you get T naught and the slope. That's what you get out of this calculation. So let me walk you through an example. In order to, and I don't know why this one is not animating, because last night I did something. But anyway, let's take a look. What you see here, just take one moment. What you see here is a value of alpha. Now it can be anything. You are starting a calculation. It can be anything. So put whatever your initial guess is, you put it here, and beta, you put it here. And alpha and beta are these two values. What are these? These are the way that the student passed and failed. So you have in your Excel spreadsheet a column, the first column, let's say, you have 0 and 1, depending on the student passed or failed. The second one is the number of hours studied. Now, you will calculate this column. How would you calculate it? You know the alpha value, you know the beta value. So, alpha and beta. So, you will put it in, right? You will put that in, and x, what is x? X is the number of hours studied. So, you will put that value in also, right? If you put that value in, you will get a value for sigma, which I write as a S column. Do you see this value? This is the value. Value of this. Now, by the way, I don't know whether you knew this, I didn't know that before, that in a Excel, if you want to have a fixed quantity, then you put this D1, if it's a fixed quantity, you put this $sign. You all knew that, right? I didn't know that. So therefore, I was putting it every time I was changing the value. But anyway, so these are the constants. And what is B5? B5 is this column, which is your X. So you evaluate it. You get a set of values. Now, that's not what we are interested in. That's the sigma value for 1 point. That's not what we are interested in. We are interested in here. So therefore, what do you have to do? Yi is in the first column. Sigma is in this column, and 1 minus y and so on and so forth. You can calculate that, and these will be that value, right? For every value, every point, you have that. And what is the error function here that I wish to minimize? Is essentially sum of all this. And what is the answer? 14.72, let's say. Now, do you realize that if you change the alpha and beta value, then you will get a new this? And what you do is play with it and until you get the minimum value. That's how you will get the value that sort of does the classification. Now, it turns out this is where the computer scientists come in. They essentially have gradient descent, various types of Newton method for very large matrix. That's what their research is all about. How to sort of take the alpha and beta in a way so that it goes to the minimum point relatively quickly. That's what they are all trying to do. But you see, this is what they are doing. All these humongous things, there is nothing more sophisticated than this. So, for example, there are many websites that does this. For example, this is the data. Remember that 0.001, 0.5, 0.75. Those are the number of hours studied. 0.00. This is the whether you passed or failed. And you copy paste in this same calculator, it will automatically do a bunch of iteration. And these iterations have a name called epoch. Epoch, do you know what it means? It means sort of generations, sort of. So you are successive generations of iteration. You are sort of evolving, they make it sound very mysterious. But at the end, the answer is, of course, what you got before. That study 2.7 hours, you have some chance of passing. And if not, you are in trouble, right? But you get the algorithm. This is what they do. Now, let's make the problem a little bit more complicated. I'm trying to get this because these are sort of the elemental things of classification. Let us make it a little bit more complicated. Let's say if you study too much, then you fail also. Meaning that you come to the class and you are so tired, you cannot think straight and you fail again, right? It turns out that this is a fundamental classification problem that is related to XOR. And I will connect it to the Karnaugh map in the next class. But so this is sort of classification where you failed if you do too little, if you fail if you do too much. In between is a sweet point. You want to do the classification. How will you do a machine learning in here? In order to do machine learning in this one comes to a very fundamental thing. So you can see this is what we are trying to represent, which is that if you study too little, you are in trouble. If you study too much, you are in trouble. I want this group, a small group in a vast space. I want a small region classified where rest of the region is one group, fail group, and in the middle there is a pass group. How do I handle that? Because you see, you can immediately see the trouble. Sigma, a single sigma cannot handle it. Single sigma on the left-hand side, it has failed. Single sigma on the right-hand side, it has passed. So therefore, single sigma could not do it. So you can immediately see why I may need 2 sigmas, or 3 sigmas, or 4 sigmas. So this is how my deep learning is gradually will be coming in. So let's say Y1. Y1, you see, I have a mu1. That's how many hours you studied, and W1 is sort of the transition point, and so on and so forth. And so you can fit this one for mu1. Think about, make all of them pass, the ones that failed, so you make them all pass. So you can get your first function fitted. Then what you can do is that everybody who is starting mu2 and all, everybody who failed, make them pass and make all of them fail. So then you can fit this function, which would be this function. And then you can see that y2, you flip it, you do this will become -2. And if you add these two, then this will become the group that passed, right? Because this is y1 minus y2, then y1 plus minus y2, that gives you this. So therefore, you can see what happened. This is my new machine learning 2-node problem. Because if I do it with W1, where did I get a W1? This is my weight. If I get a W1, then I can construct a function which will give me a sigmoid, which is this blue sigmoid. And if I go along this one, I will get a red sigmoid or salmon sigmoid. And with the W4, with a -1, I will do the flip. And when I sum, do you see that my machine learning algorithm will now tell me that this group of students, 1.5 hours and maybe 4 hours is how much you should study. You should not study beyond that point. So this is how a 2-node machine learning thing comes. Do you see machine learning this is a representation of F that will give you between the input hours and output pass-fail connection. That's what it's trying to do. Now it turns out, what is remarkable, that it doesn't have to be any simple thing. It can be anything you like. Let's say you have mu1 to mu2, one group is passing, another group is passing with between mu3 and mu4, whatever you want. So you will have a pair that will mu1 and mu2 that will allow this to go. Remember that this one would be -1. Then you have mu3 and mu4 which will represent this function. And very soon you realize that it really doesn't matter. I can have arbitrarily complex function and with a single layer I should be able to reproduce it. So there is no trouble in terms of representing any function that I want. If I given this information, the data, that who passed and who failed, and how many hours to study, then I can simply increase this number of this and can arbitrarily represent any functions. This is very important because people often say that you need deep neural network in order to represent it. That's not true. At least for most of these things. Of course, what will happen, as you know, I'll show you in the next class, that if you try to do it all in a single layer, the number of these will increase very, very quickly. Do you remember that if you want to integrate a function, if you want to use Simpson's rule, then if the function is varying very quickly, then you have to take many input points. That's what you're trying to do. That's why this is not very efficient, and therefore when you have a half a second or 1 second between clicks, then you may not want to do this. But theoretically it's saying that this is the most general machine learning functions. It's clear, right? So far, I told you about one input and one output machine learning. Inside, it can be very complicated. But, of course, it doesn't have to be one input. It can have 2 input, 3 input. How does those things come? Because if you can sort of see 2 input, then you know how to do million input. Because you already know now that there are some functions like this which cannot be done with one node. One node is not possible, but you may need higher nodes. And in fact, what you can show that if there is any abrupt delta functions in here, then you know it's 1957, it was proven that if you have an abrupt delta function, then at least you need 2 layers in order to do it. But more than 2 layers is not necessary. Do the homework, because you will figure out many of these things yourself. It's no rocket science. Alright, so one example problem is, let's say, 2 input, where you have a solar cell. Solar cell is, as you know, converts sunlight to electricity, and let's say the power is degrading over time because the solar cell is aging and things are getting worse. And let's say that it is a function of relative humidity and temperature. You know, high temperature, it degrades faster. If it rains a lot in India or in Indonesia, then it will degrade a lot also. So let's say 2 input in that way. And let's say you have you are collecting data. You know zero physics. Remember, machine learning means you have not done any physics. And so only thing you can do is simply ask that after end of 3 years, who has survived and who has failed, and you are collecting the data, just like students pass fail. Which solar farm has survived and which has failed, and let's say these are all fails. These ones all fails, and these are still working. Why? Because you sort of know that low relative humidity, low temperature, chances are that they will survive. So somebody is asking that I want to do it new solar cell installation at this environment, which is somewhere, some part in, let's say, in Indiana or whatever, and will my thing pass or fail? Now you can immediately say, just by looking at it, that it is going to fail. But of course, machines are not so smart as you, right? Because you have an eye, which is a sophisticated machine. Machine doesn't have an eye, so therefore it has to draw a straight line, a line of some sort. So what line will it draw? It will draw in 2D. Previously I drew a point which was sort of class, fail class, pass class. Now I'll do a straight line. And in the straight line, if you are on the right of the straight line, then you fail. And if you are on the left of the straight line, then you pass. And do you see that you will try many different things? You will try different straight line angles, push it left and right. And what will be your goal? To reduce misclassification, right? Who are misclassified? These two are misclassified. So you're trying to reduce the misclassification. So you can see this is probably not right. I should probably push a little bit more, because otherwise it has still some. But anyway, you get the idea. So what is the equation of a straight line? W1RH, relative humidity, plus W2T is equal to C1. That's your equation of a straight line. And if you wanted to do a sigmoid function, then how would you do that? This is like a transition, threshold point. So what will you do? You will do W1T plus W2 relative humidity minus C1. And this divided by sigma. The sigma tells you the width of this distribution. Right? What is width? Width is between this and this. At this point, there is some probability of success, leaving, and at this point, there is some probability of failing. So you do that. And then you can immediately see, you put W3 with W2 with T, and W1 with relative humidity. I'm sorry, it should have been the other way around, right? W1T and W2 relative humidity with a threshold of C1, and that will tell me whether the new farm will pass or fail. So this is a 2 input, 1 hidden node machine program, right? And it is called an artificial neural network. This is just to make people afraid. So they put all these names so that you are afraid and don't think that there's nothing neural about it. It looks like a neuron as if you have 2 input and it is connected to another neuron. So they give it a name. So this is how language often is used for the perverse purpose, not to communicate, but to confuse.
Is it a typo that you've changed the coefficients?
Yeah, coefficients. It was for you to seeing whether you are paying attention or not. All right. And what is backpropagation? In the next class, I will work it out through a clean example about how backpropagation works. But backpropagation is essentially you keep changing W1 and W2 until this has the least amount of error. It is just a curve fitting thing because you have to do iteration, right? Remember the EPO. You start with the wrong line, then you change the W1, you change your W2 a little bit until you get to the point. And backpropagation is the name of the algorithm that gives you W1 and W2 that minimizes the error. That's what backpropagation is. Now, why is it called backpropagation? Well, you do a forward thing to calculate with a wrong W1 and W2, and you will see you have made a big error. Then you will go back, and then fix them, change them a little bit, and then in here. That's the back. What is the propagation? Propagation is actually often you will have multiple layers of this. So you start from the end, you correct the first outermost layer. Once you have corrected the outermost layer, then you come one level in, then you correct another layer. So that is what backpropagation is. I'll give you examples. It will become crystal clear to you. Now, just a very quick point. So sigmoid function, it started this way, is what I explained to you. But of course, there is no a priori reason you have to use sigmoid. You can use any function that goes from one level to the another level. And often people use tan hyperbolic also, because tan hyperbolic also goes between 2 transition points. By the way, does it remind you of something from solid state? Fermi function. So sigmoid is Fermi function. If you want to impress your friend, you should write, I fitted my machine learning artificial neural network with Fermi function. People will be impressed. Now, tan hyperbolic, only difference is that it makes things symmetric. So often convergence is a little bit easier with plus and minus. And if you are the homework that I have asked you to do in terms of TensorFlow, then you do that, and then it becomes easy. And then, but of course, you don't have to do tan hyperbolic. You can do a shifted sigmoid, which has also done the same thing if you do it minus 0.1. So you do minus 1 and plus 1. That makes the matrix symmetric rather than 0 and 1. So it makes a conditioning and other things. But often these days, people use a slightly nonlinear function, and this is the most heavily used function these days, because what you may want that all fails are equal, but all passes are not equal. Meaning that you may not really want to say that the student who got a 95 is the same as the student who got 65. That's a little bit unfair. So in this case, but whoever got below 33, that was our pass point when I was growing up, they are all the same. They did not study. But in here, you may want to do a little bit more. And it turns out that when you write this backpropagation functions, some of these functions converge much faster compared to others. So these are all empirical games people play with. There's no proof on other things that people strongly. They will different try. If you want one, you can try it, and if it runs faster, then you'll be famous. There is 2 other points I want to make about this in 2D. One is that I already introduced you sigmoid. You understand that, right? So this line, you should think about it. It's like a valley, and this is like a mountain, not a mountain. What is it? Flat region, plateau, and this is the edge of the plateau. Had it been a sharp, from the valley to the plateau, a sharp transition, then this width of this region would be very narrow. But rather, it's a gradual up, and so that's how this one looks like, and it's symmetric. You remember sigmoid function is symmetric on both sides. But the problem on these ones is, I mean, this is fine, but there is something called, which is a little bit better, requires a little bit more computation, but is sort of a little bit more robust. It's called support vector machine. Now, the second I thought this must be something sophisticated about vector vector machines used to be that when you want to do various types of, it's a computer class, right? It has got nothing to do with that. Actually, it turns out this is support vector, means there are two friendly vectors which will help you to make the classification better. So support vectors means two vectors. So what are those two vectors? What this one says that instead of trying to minimize the misclassification error, what you should do is to take the points which are edges of this misclassified, edges of the properly classified one, and draw a line through it. That's one of your support vector. And then the other ones which I have also on the other side, you draw a line through them. That's your second vector. And then you try to draw a line. This way, the classification would be more robust, that you are sort of accounting for the edge a little bit more properly, rather than you are trying to just draw a minimum line somewhere else, right? So the support vector machine, there's nothing machine about it. It is simply two vectors that is helping you to classify better. That's what support vector means. And this linear rectifying unit, do you see that? That here the line up to this point, they are all the same. Unlike sigmoid. Sigmoid was already transitioning. Up to this point is the same, and then it keeps going. So it's no longer a plateau. It's sort of a linear ramp going up, and so that's how this one is accounted for. These are sort of terms. You can see there's nothing complicated about these terms. Just once you know it once, then that's it. So let me summarize then. So this is really part one of the two parts, because in the next one I will show you a few more related to backpropagation and all those basic concepts. But I hope I explained to you that this is very good for classification information. And it is very important that you remember this. Machine learning is empirical. And is empirical, and therefore is very easily generalizable. And most of the time machine learning becomes complicated because only thing it has is straight line. It doesn't have anything else. It has only straight line. Because you remember W1, W2, even if you had multiple layers, it will always be W3, W4, W5, W6. So linear multiplication. And that quickly expands it. Why linear? Because that's where the algorithms are most efficient. Backpropagation algorithms are most efficient. So that's why it is done that way. So it's a curve fitting, and curve fitting is never good for engineering. It's good for business and this and that, for various things, but not for us. And then I hope you'll remember that any function can be represented by a machine learning. That's a general theorem. And I explained one or two, but you can get that here. If you have more, the same algorithm, same on in TensorFlow homework, you'll be able to have that. Take a look at the questions quickly, and then we'll wrap it up today. Sigmoid functions and tan hyperbolic functions. I hope you remember both symmetric, but perceptron. Perceptron is another way of that circle thing. That is called perceptron again. To give you a feel that it's complicated. Now, I think some of the support vector machine, I hope you remember. In what way singular vector machine is better than sigmoid transition function? Answer this question. These things would be in the final. I'll ask you this. What is the loss function? I hope you remember. MAD loss function, normal loss function. And this accidental misclassification is the reason why sigmoidal and okay, that's all I have today. In the next class, we'll pick up